This is a video introduction to the main phenology code that generates the phenometrics from the data from each tree that's been extracted from the set of imagery for each date. And so the starting point of entry to this script is a file folder full of CSVs, one CSV for each image date, and then the rows tied to UIDs, meaning the unique ID of each crown. So this code ingests all of that and does a bunch of things that I'll show in a second. So first of all, this is also a good time to talk about my code structure, which is not perfect, but it's okay, and it's good to keep things consistent. I always start with this 0, description and then have these little lines next to it. And so what those little lines do is they will make a entry in this little outline area. And so I only use the lines next to these enumerated lists and nowhere else. So this is nice and clean over here. So you can get a real sense of what this script is going to do. And you can, even click on the areas to go to them more easily. So description, we've got inputs, outputs, etc. You can run this script all at once, or your starting point will be to run it using selecting code and hitting Control Enter, so you can spot check things. This work requires a ton of spot checking to make sure that no errors are getting away. So O1 is always the libraries, so we'll load up these guys. O2 is always the user data. And so this should be the only place in the whole script that a human has to interact with to put in parameters. If they have to interact down here somewhere, it's not going to work. People will forget and get lost. So all the user parameters are up here. We're going to set the working directory. The reason I'm setting it here is simply because this script is in this folder right now, and also this helper script is in there. So as long as this script and the helper script are in the same folder, you would just set the working directory to whatever that folder is. So we'll set that, grab the helper script. I'm not going to talk about all of these things. You can read the comments. There's a lot of them. But I'll talk about some. Output directory, this is going to be where the results are written. And so we are going to change this from Denver to DC. This JPEG outputs folder already exists, and you would need to make it if it didn't. So now this is going to change our working directory to this output directory, which is fine at this point. This is important because this is the folder where all those CSVs live, and so this is our phenosensitivity extracts from earlier this year. So great, run that. We've got the output file name. This is double logistic. PSS4 is PlanetScope 4-band. This is the year that you're running. This code only runs 1 year at a time for now. And this is the date of creation of this. So this is what? This is 5/15. 5/15. So we'll run that. This below user, let's see, did I even run that? User year is where you actually specify the year, so 2018. Season window, this is where you specify if you want to pad the beginning and the end of the year to include more data to make the fit better, to establish the winter baseline values a little better. So usually I would go, ideally I'd do like 2017, December 1st or something like that, but we don't have data from 2017, so I can't do that here. But I do then extend all the way to March 5th on the front end, which definitely helps the fitting. And then this other stuff is more housekeeping and computational stuff that we won't talk right now. Then we've got our rarely changed parameters that you can mostly just run, but good to read over at some point. Now we're loading the data. So the file list is going to be the big list of CSVs that you specified the file path for above, and it's all going to load using Vroom is going to bring in all those CSVs, bind them together into our DC DAT, which is our big data frame that has all of the trees. This probably at this point shouldn't be called DC DAT because it's generic to any city, but oh well. So it has loaded. Now let's just take a look at it. Head DC DAT. Okay. We see that that is looking good. It's got some data. Interestingly, it already has a year column, so this has been an issue for me. I'm just going to comment this year column add-on for now. Hope that works out. Do some other things I won't talk about. And then we're moving on to setting up the parallel cluster. And so this is what uses your computer's multiple cores to process multiple crowns at the same time and speed things up dramatically. And so this unique UID unique is getting the set of unique UIDs, unique tree crown locations from the data. And that is the basis for the loop that will follow. All right, so this marks the beginning of the parallelized loop, but we're not starting with that. We want to just look at a few individual crowns. And so this is where you might go into ArcGIS and find your crowns. They find an interesting crown that you want to examine, find what its UID is, and just enter it in here. And so now we're going to do just Control Enter to run individual lines. And in this case, you would not run this line. This is for when we're in looping mode, going through iterating through each crown. All right, so user UID is now 55339. And go down and we will select only that tree now. So we've gone from DC DAT with all of the data to tree DAT, which is just one tree in 2018. So 62 observations. If this number is 0, then something has gone wrong. We'll do some other stuff to clean up the data, remove some outliers. You can look at the specifics, and then we've got these diagnostic plots. Now, these do need to remain commented anytime you are running the loop. Otherwise, things will get very bogged down. But for diagnostics, they are here. So the first thing we are seeing is the data and the final spline fit. And so the initial spline fit was used to find outliers and eliminate them. This spline fit is actually used to calculate a set of like the Bolton 2020 style percentile-based phenometrics. So make sure you are familiar with what those are and how those are extracted from a spline. So we'll continue now to parameterizing and running the Elmore double logistic fit. And we run it 3 times so that it reweights each time, always moving the fit upward with the assumption that low NDVI values for a given time frame are probably bad. High is good. High means no atmospheric contamination. Low means likely some atmospheric contamination or a geolocation error where the pixel is actually a piece of sidewalk or something. So then we'll uncomment that code too, and now we'll look at the double logistic fit. Why this is not a line, I don't know, but whatever. So you can see that the fit maybe isn't quite as good as the spline fit, but remember the advantage here is that it's parametric, meaning that you can decompose this curve into 7 parameters, some of which have ecological meaning. So I want to make sure that you understand those from Elmore 2012. The rest of this bootstrapping, this is just to be able to randomly sub-select from the data 50 times and then be able to create a plot that has both a mean fit from those 50 iterations and the standard deviation of the fit as one way to show our certainty with the data. So I'm just going to run this loop. Oops, I think I missed it. There we go. Here's the end of the loop. So it runs that 50 times. Now we're just going to gather, extract a bunch of information and phenometrics from this loop. And finally, this is going to, whenever you're running the bootstrapping mode, so your boot iterations are greater than 2, it's going to create a plot for you. Why am I telling you that? Well, when you're running all of your crowns in like operational mode, meaning thousands of crowns, you will turn off bootstrapping because it takes too long. And so the bootstrapping is just for a subset to characterize the error of the whole set without having to do this on the whole set. So what happened? What did this create for us? JPEG outputs, plots. You've got our UID up here. It is a, what is that, a sugar maple, I think. And you've got our fit with the error bars from the bootstrapping. And you can see, like, in some places there's very little uncertainty, but in some of these shoulders, like if you remove some of these points from the random sample, you're going to have a lot of variability in where that shoulder ends up. So these are great diagnostic tools that you can turn back to without running the code again. So that's kind of it for running a single tree. Like a lot of this stuff is all just gathering up all of these metrics and putting them into a data frame and ultimately writing things out to disk. So now I need to remember to I just do Control Z because I know the last thing I did was to uncomment this. So we do Control Z and it comments them again. Control Z and it comments those. And ideally I go and I comment this out too, but it doesn't matter because it would be overwritten by this next line. Anyway, so I don't think you need to worry about running a lot of crowns right now. That would be inefficient. But it might be good to get up and running on one, and then we can talk about running this on a small, like a 1% sample or something when that becomes useful.